Hey there, this is Naveen Kumar Macha from University of Missouri, Kansas City. I'm a PhD student. I work here at Nanocomputing Research Group. I'm going to talk about our solution to the microelectronics challenge, that is interconnect crosstalk based computing for secure authentication in autonomous system. First, I will talk about our crosstalk computing approach, then about its application into the security. So we know that innovation has been the hallmark of semiconductor industry's progress. So the crosstalk computing is a very innovative and a novel way of doing computation. We actually do implement the computational circuits in interconnects in contrast to the switch-based computation in traditional approaches. So let's look into the brief overview of this crosstalk computing concept. Imagine we have three metal lines arranged like this, and they are coupled through a coupling capacitance. When there is a signal transition on one metal line, it induces a voltage onto the neighboring metal line. We call this aggressor-victim scenario. So the voltage induced onto this victim metal line is actually proportional to the coupling capacitances that we have here. So similarly, when there is a transition on both the aggressor nodes, they induce a voltage onto this victim metal line, which is proportional to these coupling capacitances. So now we can think it in a way that the signal induced on the victim node actually has the information about the signals on the two aggressors. So we astutely try to engineer these information to implement logic gates. So let us see the intuition behind how we can implement the logic circuits using this concept. Let us take an AND gate. So we choose a coupling capacitance here in such a fashion that either 1-0 or 0-1 transition on aggressor metal lines induce a voltage onto the victim metal line which is below a selected threshold. So the selected threshold here distinguishes logic 0 and 1. So now, however, when there is a 1-1 transition, they induce a voltage on victim node which is above that selected threshold, which can be considered now as logic 1. So this is how we can realize the AND gate behavior in this crosstalk coupled interconnects. So how can we implement OR gate? Now, by increasing the coupling capacitance between these aggressors and victim, we can create a situation or a scenario where the transition of 1-0 or 0-1 are now sufficient to induce a voltage which is above this selected threshold. Therefore, we can create this behavior of the OR gate just by playing with this coupling capacitance, which can be tuned by playing with the dimensions or dielectric. So, can we do more with this? Can we implement more logic functions? So just by increasing the number of aggressors and playing with these coupling capacitances, we can actually create many patterns, many patterns of complex logic gates and actually also reconfigurable logic gates, which I will show later. So here is the brief overview of this crosstalk computing fabric. So down here we will have the substrate on which we will have these active devices. So the active devices here will be used to maintain the signal integrity in the large scale circuits. And then on the top here is the crosstalk coupled interconnect fabric where actual logic gates, logic computation will be implemented. So here is the rich set of logic functions that are implemented in crosstalk computing. So starting with the basic functions, we have covered up all the complex logic functions. And interestingly, we can have the reconfigurable feature in this crosstalk computing at very fine-grained level. So, for example, an AND gate can behave as an OR gate, a sum circuit can behave as an AND gate, OR gate, etc. So these are the rich set of reconfigurable circuits that we have implemented. So what are the potentials of these circuits? Well, we can use them to implement very denser circuits since we are just using interconnects. So these denser circuits can result in, can address the saturating Moore's law. Now, as I have shown, we can also implement reconfigurable circuits which can be applied in multifaceted applications. So, for example, they can be applied in cybersecurity to design the secured or security enhanced hardware circuits. and they can be applied for resource sharing, and they can be applied in fault tolerance. And as in traditional way, we can also use these reconfigurable circuits to design reconfigurable systems, and they can be also used to design radiation hardened circuits. So now our solution to this challenge is in the area of cybersecurity, so which I'm going to discuss now. So the application that we chose to implement as part of this challenge is implementing an authentication block that is a secured hash algorithm block in a chip. So these SHA algorithm are used for authentication purpose in security. So here is the brief overview figure which shows what an SHA is. For example, think you have a sender and receiver here. So, and this is the encrypted message here. So when we send this encrypted message to receiver, when the receiver receives that message, we not only need the data integrity, but we also need authentication. To maintain this, what we do is we send this message through this hash function or this SHA block, which will generate a message digest or an hash code. So now this hash code will be appended to this message, and this message will be sent to the receiver. At the receiver end, we strip this hash code and send the message through this SHA block, which will again generate this hash code. So, and we also take this hash code from here and we compare both of these hash codes. If they both match, that means we authenticated the origin of this message as correct one. So where can we apply these secured hash algorithms, or where can we apply these SHA based blocks? So well, they can be applied in our modern day electronic fund transfer methodologies. It can be applied in authenticated electronic data transfer. It can be applied in encrypted data storage, authentication in IoTs and in blockchain applications. So yeah. So this is the architecture overview of the architecture that we are going to implement is this SHA 512 block. So what it does is basically, starting with the message, initially we do some pre-processing steps where we pad some extra bits that are needed to process the data, and that padded data we actually pass through a word generator which generates a word which is function of this input message. And now we will also have some ROM blocks which generate some random constants that will be used later. So here is the hash function or the round function that implements the actual message digest function. So it takes as input these words and these constants, and it goes through series of computations which will finally generate a hash code. So the blue blocks here are sequential blocks, and the green blocks here are the computational blocks which we use crosstalk computation, in which we will use the crosstalk computational circuits. So here is the overview figure of these two circuits, the word generation block and the round hash and the round function block. So for example, we need set of XOR gates, and we also need some majority gates, some modular sum blocks and XOR gates, multiplexers. All these combinational blocks we implement with the crosstalk computational circuits that we have implemented, and these blue blocks are the sequential blocks that will be implemented. So these implementations, we project from them from our pre-circuit evaluations and the designs, we project the benefit of 5x reduction in the area and density, and 2x reduction in power, and 1.5x improvement in performance. So thank you.